Hey everyone, welcome back and let's write some more Leetcode today. So today let's solve the problem, maximum score from removing substrings. The idea is that we're given a string like this, and we're also given two hard-coded strings. Each is of size 2, so AB and BA. Now the score associated with this string is 4, and the score associated with this string is 5. So these are the parameters, these two and this. These are not going to be given as parameters because like I said, they're pretty much hard-coded. So the idea is that by removing this substring from the input string, so suppose from over here, we gain a score of 4. By removing this string BA, suppose from over here, we gain a score of 5. We want to try to maximize the total score that we can get, and then just return that score, not the string after making like the removals, just the score. I'm going to kind of go through two different solutions to this problem. The first one is going to be a linear time, linear space solution. The second one, we're not really going to go in super depth. It's more about how to optimize the space complexity, which is kind of hard to do with this problem just because the nature of it is a string. And strings are immutable, so anytime you want to make a modification to it, it's going to be a linear space operation because you're going to have to create a new string. But we will kind of talk about that because it's very similar to a Leetcode easy, believe it or not, because I think that kind of optimization is actually simple conceptually, so it's worth going over. Even getting into the first solution, it is somewhat difficult. So I'll be focusing on why does it work, as we usually do. I'll also be trying to guide you a little bit towards how you can try to arrive at the solution, even though I'll be honest, it's not easy. Like I can't just give you a 1, 2, 3 step book on how to exactly solve problems like this. I wish it was that easy. Unfortunately, it's not. Now, getting into the problem, I think it is somewhat obvious that the scores matter. Like at some point, we're gonna have a choice to either remove AB and BA. I think that much is obvious just because, I mean, look at these two strings. They're kind of the exact same. Like imagine if we had an input string that looked like this, A, B, A. And when you kind of look here, we kind of do have that in this string. So this is kind of where the choices come from. We can possibly remove AB or we could remove BA. Obviously, we want to do the one with the higher score, which we don't necessarily know which one is that. Like we have to kind of determine that ourselves. It's not always going to be this string. In this example, BA is the string that gives the higher score, but it could be inverted. This could be 4, this could be 5. In that case, we'd favor this guy. So obviously, this starts to feel like a greedy problem, and it actually is. And the solution is actually very, very simple. If I showed it to you, you'd think, wow, that's really it. But that's not the hard part. The hard part is, well, why does it work? So I'm going to kind of get into that first of all. First, let me show you why a different solution won't work. If we try to solve this problem, the first observation you have to make is that both of these strings are of size 2. That's a very important observation to make. Let me tell you why. Imagine we have one pointer. We're iterating over the input. We want to know, do we have a matching pair? Like if I'm over here, I want to know, do I have a matching pair? All I need is the previous character to know if I have a matching pair so far, right? So that's easy. That's great. We just look at the previous character we saw. Is it the same? Okay, great. And now suppose we wanted to actually remove this. How do we do it? Consider this. Consider we're adding all of these elements to some data structure as we go. And now we're going to just skip adding this one. We're not going to add it to that data structure. And not only that, but we're going to remove the previous character that we saw. Does this sound familiar to you? Does this sound like we're getting towards a data structure that you might know of? Yes, it's called a stack. That's how we solve this problem. This is of size 2. We only remove the previous character when we want to remove one of these pairs. This is another key observation you really have to make to solve this problem. But even that is not enough. Because again, the hard thing is we have choices. And even more, if I remove a pair, like just look at this string right here, BBAA, look at that string. All I see right now is one pair in it, right? We don't have any occurrences of AB. This is the only pair I see. Now, what happens when I remove it? Boom, boom. Well, the new string becomes BA. Now we have a new pair. So the hard part about this problem is that removing a pair could potentially introduce new pairs. So again, another reason why the stack is necessary. And now You might think you have a solution. You might think this. Imagine we have some string like XYZ, A, B, A, X, whatever, right? This is just a random string, but watch this. We go through it. We get to A, okay? Like this is added to the stack so far. We get to B, okay. We see. We now have a matching pair. Beautiful, right? We should remove it, shouldn't we? We get a score of 4. No, not yet. Because before we try to do that, let's just check. Okay, I have a B right now. If the next character is an A, which it is, and if the score of removing that type of pair is even greater than this one, which it is, then let's not do this. Let's not remove this pair. Let's skip it because by the time we get here, we can remove that pair. So basically, you might think that there's a way to solve this problem by iterating through it a single time and just trying to prioritize whichever pair that has the higher score that gives us, right? So whenever we come across a choice, like a decision, we favor the one with the higher score. You might think this will work. Let me give you a counter example. And it's literally the second example in this problem. So I just have AB here to show that it's the one that associates with this, and BA is the one with this. So the answer to this problem is 20. How do we get there? Well, look right over here. When we're over here, like when we're at this B, we're going to then get to A. We're going to see, okay, we have this string right here, BA. We see that it's the one that gives us a lower score. So maybe we can form a better string with this A. Maybe we can form AB. Nope, the next character is also A. So then you might say, okay, well then we have no choice but to pop this and remove the string BA, even though it gives us a lower score. Nope, you made a mistake. Let me show you the better way to do it. Look, these two are fine as is. Get to the second A, then remove AB here. The beautiful thing about that is then we kind of get rid of those, and then we can join this A with this B over here. Let me make the string just a little bit bigger. This portion is what we're specifically focusing on. We have the choice of a BA, but that's not what we want. We want the AB. Get rid of this, and now we have another one, another AB. Get rid of that again. That gave us a score of 10. If we did not do that, this is what we would have had. We would have had the BA, okay, and then we would have had the AB. That would have been a 9. So clearly, the approach of just looking at the element and comparing it with the previous one and potentially looking at the next element is not going to work. The approach that will work is this, a two-phase approach. First, remove all occurrences of the one that gives us a higher score. So go through this input string, which I'll quickly draw, and only remove instances of A, B. So let's iterate. We have an A, we have an A, we have a B. Okay, compare it to the previous one. It's an A. Get rid of these two. Great. Now we're at B. Check what's at the top of our stack. It's an A. Get rid of these two. Now we're at A. We keep going anytime we have like non-AB characters. Notice that these are characters that will never be removed. Therefore, any character on this side of the wall and any character on this side of the wall will not be able to join each other. I feel like there's a political analogy somewhere in here, but I'll try to skip that. We're at B now, and we're going to keep going. B, A, well, there is a pair, right? But remember, this is not the pair we're looking for. We're only looking for ABs right now. So again, just skip it. Now we're here. Now we're here, remove this. Since it's a matching pair, now we're here, check the top of the stack, remove this as well. So now we removed 4 pairs, each gave a score of 5. Now, the second phase of the algorithm would be removing all occurrences of the other type of pair. Now in this, that does not exist, but I can show you an example where they could have existed. We could have had an extra B over here, and there's no way that we would have been able to get rid of this because there's multiple consecutive A's over here. We deleted everything over here, and this is like a wall, like I kind of said. So this would have remained, and in the second phase of the algorithm, we would have gotten rid of this. Alternatively, or in addition, there also could have been an extra A over here. We removed this portion. This is the wall, so no way this would have gotten deleted, and this would only be deleted in the second portion of the algorithm where we would gain a score of 4 from it. Okay, so now, if this makes sense to you, that's great. You can start coding it up, but there's one question you might have forgotten to ask me. How do you know that after the second phase of the algorithm by removing some BA pairs, how do you ensure with 100% certainty that by removing these in the second phase of the algorithm, we aren't introducing any A-B pairs? Because it's okay if we introduce an extra BA pair in the second phase of the algorithm. That would look something like this, where we had a 2 A's over here. So imagine, something like this. This would not have gotten deleted in the first phase of the algorithm. And in the second phase of the algorithm, it would. We would have deleted this, and then we would have found this matching pair and deleted it as well in the second phase. But how do you know for sure that by doing that, we're not introducing any pairs of the first type? Because if we are, then we better delete those too, because that's the only way we can maximize the score. So how do you know? Well, the answer is some examples. Let me show you. Let's consider these two strings and really dig deep. Consider if this was the first phase as it was when I went through this example. There's a few possibilities. We remove these two characters, but what's on either side of them? Now, suppose it's like a non-AB character. That's very easy because, of course, that's not going to introduce a new pair. If even one side has a non-AB character, it's not going to introduce a new pair. I mean, how could it possibly do that, right? I don't think I have to probably go in depth, but if you have questions about that, feel free to make a comment. Like I said, any non-AB character is practically a wall. So now we realize that we only care about the cases where there's ABs on both sides. Now, there could be an A on each side, there could be a B on each side, or it could be something like this, AB or BA. I think it goes without saying that in the first two cases, we're obviously not creating new pairs. Isn't that right? Okay, so let's go to the second two cases. Hypothetically speaking, if we had something that looks like this, then we delete this, we obviously created a new pair, AB, of the same type, right? So we know with 100% certainty that that new pair that we just created is also going to get deleted. So that's another simple case, right? We don't even worry about that. You saw that happen right over here. So go ahead and delete this. Forget about it. Okay, but then the other case, by deleting an AB, we created a new BA pair. Is that a problem for us? Not really. This is the first phase of the algorithm. Like I said, if we create a new BA, that's perfectly fine. That's going to get deleted in the second phase of the algorithm, right? So we just went through every single possibility, and I proved to you there's nothing wrong with deleting these in the first phase of the algorithm. So go ahead and forget about all the cases. Now I'm going to run through the exact same over here, and I'm about to blow your mind. Going through 4 cases, remember that the first 2 are pretty trivial, so we kind of just skip those. So now look at the next 2 and pay very close attention. First, I'm going to go through the last one over here. Imagine we delete a BA. That's perfectly fine because we're in the second phase of the algorithm where we're deleting all BAs. I delete the first one. Okay, I just created a second one. Who cares? Delete that too, right? So nothing wrong with that. Now, watch this. This is the case we want to avoid. Oh my God, we deleted a BA and we somehow created an AB pair. But oh no, the first phase of the algorithm is already over. We created a boo-boo. Nope. Let me tell you something. There's a concept in mathematics called proof by contradiction. I've been wanting to make a course on this for so long. I think I mentioned it at least a year ago. But there is a concept called proof by contradiction, and I just did it for you. Look at this example I just showed you. How could it ever be possible that we have a substring in the input that looks like this? Didn't I say we deleted all AB pairs? So you tell me, how the heck did we get an AB pair in the second phase of the algorithm? How did we have a string that looks like this to begin with if we deleted all of them? This is a proof by contradiction. This case will never exist. Therefore, we only need 2 phases of the algorithm, which will guaranteed to delete all AB and BA pairs. And if this seems complicated to you, I just want you to know that this is the hard part about greedy algorithms. Implementing them is usually very easy. proving why they work is the difficult part, but almost always you can use the technique called proof by contradiction to do it. I really hope I get the chance to make a course on discrete math for you guys, and let me know if you'd be interested in seeing it. So now let's code up the solution to this problem. It's going to be linear time and linear space because we're using a stack. Okay, so these are kind of the notes that I took when I was solving the problem. They may or may not be helpful for you, but I hope that the explanation that I just gave was actually helpful. Okay, I have the code here. Let me delete that as well. Sorry about that. But the idea is that if we're going to do this algorithm in 2 phases, we should probably create a helper function for us, which I'm going to call remove pairs. And so there's 2 things we want to keep track of. What's the pair we're trying to remove? That's either going to be AB or BA. And what's the score associated with that pair? Once we have that, this is how we can use that function. Just assume that this is going to remove the pairs from that string, and it's going to update S. And the way it's going to do that is by, I'm going to declare it as a non-local variable, something like this. But if you wanted to, I think you could also do something like this, like self.s is equal to s, like set it as a variable for this object or class or whatever. But I'll do it like the non-local way. It doesn't really matter how you do it. And this is going to return the score we got by removing those pairs, and then it's going to update the string in place. Assume that that function works. This is how we're going to use it. We're going to have our result initially. It's going to be 0. This is what we're trying to return, but we want to update it. We want to do something like this. Like we want to add to it the function call, and we want to do like AB and whatever score is associated with AB, and we want to do the same thing for BA and the score associated with that. The only problem is we don't know what order we want to call these in. If this score is higher, we want to do this first and this second. But if this score is higher, we want to do this one first. How do we know which score is higher? Well, for that, we have if statements, don't we? So I'm going to do something clever. I'm going to say the pair is equal to AB if X is greater than Y. Otherwise, I'm going to set it to BA. And so this pair is what I'm going to pass in the first time. Okay, but well, what score should we do? Do we need another if statement for that? If you like if statements, go ahead, but I like to keep things concise, so I'm going to go ahead and use max of X and Y. We already know we found the max here, so this is the one that has the max. In the second part, we can do the min of xy. That's straightforward, but what do we do for the pair? Well, just the opposite of whatever this was, aka reverse it. So something like this. It's not really expensive to do this reversal down here because it's a string of length 2. Okay, now we've done the hard part, believe it or not. This part is going to be not too bad. I'm going to have a variable here, which is going to keep track of the score. Actually, score is a parameter here, so I'm going to just call it result again. Just so you know, this result is a different variable from the one here. They have a different scope. So just want to mention that. And I'm going to have my stack that I was talking about earlier. I'm going to go through every character in the input. We only care if this character is the second character in the pair. Because if it's the second character in the pair, then we want to ask the question, okay, is the stack non-empty? And is the top of the stack equal to the first character in the pair that we're looking for? If it is, then do something like this, stack.pop, and update the score. Increment it by whatever delta that we passed in, whatever one of these we passed into the score here, add that to the result here. Now, if that's not the case, if we're not popping from the stack, then we're pushing to the stack. So here I'm going to do stack.append the character, and then at the end, we want to return the result. Zooming out a bit, but don't forget, we do want to actually modify the string. That's why I declared it as non-local here. So how do we do that? What's the easiest way to do that? Well, you don't want to remove from a string, so we can just use the stack that we were keeping track of, and then right at the end, do something like this. The delimiter is going to be an empty string. We want to join all the strings in the stack together. So you can do that like this in Python. And I think we can then set s equal to that. And this will actually update the s that's out here. That's why I declared it non-local. And that's very important because when we execute the second phase of the algorithm, we want the string to be updated. So this is the whole code. Let's run it to make sure that it works. As you can see, it does. It's pretty efficient. Now, one last thing I wanted to mention, the more efficient space solution, and I won't code it up. I just wanted to kind of talk about it conceptually because we can't really code it up in Python. imagine this. Imagine that the input, instead of being a string, it was actually an array. How would you solve this problem in constant space if instead of a string, you were given an array? So imagine that these are like numbers or something. I know they're not. I know they're literally characters, but try to use your imagination. Well, we could then do the removals in place. How would we do it? Well, I think it's called Leetcode problem 26 or something, remove duplicates. So in that problem, like anytime you have adjacent duplicates, so like I got an A here, I have a second A. They're right next to each other. And I think in the context of that problem, the duplicates were also adjacent, like if they existed. I think the input array was sorted or something like that. Maybe I'm forgetting, but you can correct me if I'm wrong in the comments. But if that were the case, we'd do something like this. Okay, this is an A. Okay, well, just move this A over here. Obviously, the A still exists over here, but we'd have 2 pointers. We'd have this pointer telling us where to put the next character. So this B would then go over here. And then we move here, then we'd shift this pointer again. So it'd be kind of like that. So now in the context of this problem, let's say we're removing ABs. We start here, we have this A, we have AB now. What do? Just take this thing and try to pretend like it's not there. Because what we're now going to do is we're going to have a pointer here, and our pointer that was already iterating is now going to take every character we see and shift it to the pointer over there. So now the B is going to go here. Every time we do that, we're going to take this pointer and shift it to the right by 1. This would now start looking something like this. All of these would be over here. So this would be B, A, X, Y. And then this part would also be over here, BB. And then this A would also go over here. And then this AB. Well, firstly, we'd have taken the A over here, put it there, and then we'd see that we put the B here. So now we would take that left pointer. It was telling us where to put the next character, and now we'd shift it to the left by 2. So now when we see these 2 Bs, we're going to overwrite that pair that we just saw. It would look something like this. I think we deleted a couple pairs, and I think I even forgot about one of them because now there's going to be an additional one on the stack. But I think you probably more or less get the idea at this point. Like we delete this pair, we have shifted the pointer over here. So we know now that the character is going to go here. Now we put that B over here. We delete this pair again, shift the pointer so that now we'd overwrite this part. Then we'd have like this last B go over here, something like that. And then we'd say everything at the end is chopped off. That's how we can maintain the constant space because we are modifying the input instead of creating a new string or list. That's the idea, but obviously it doesn't apply to this problem since it's a string. I'll leave things there. If you found this helpful, check out neetcode.io for a lot more. I got a lot of cool stuff coming soon. Thanks for watching, and I'll see you soon.